So leading on from last session on finishing off electromagnetic induction, we just need to spend a short time looking at something called eddy currents. The whole idea of eddy currents is thinking about, is it possible for induction to take place in conductors other than wires? We have talked a lot in all the demos we've done. It's all about moving wires and coils of wire in magnetic fields, but very often you might have conductors, any metals, moving in a magnetic field that will conduct electricity, but is not a standard wire. And if electromagnetic induction does happen, then what are the effects of this? And is it sort of something that's useful or something that's not? A couple of demonstrations you might have seen in the lab. The first one here, if you take a thin aluminium plate, which is a conductor, and you suspend it on some rigid wire and enable it to swing in a pendulum fashion. And at the bottom of the swing, so where the displacement's zero, what you could do is get it to swing through a magnetic field. So you have two magnets. This is called a yoke where the magnets are in. So you have a north to south magnetic field, and this thin aluminium plate swings and it cuts through the magnetic field. Now the test you do, which you might have done in lesson, is you remove the magnet and let it swing, and you time how long it takes to come to a rest. Then if you place the magnet there and let it swing through the magnet and time how long it takes to come to a rest, you find there's a significant difference. It's not just down to random errors. There's a significant difference, a repeatable difference in the times, and it will be slower. It comes to rest much faster in a shorter time with the magnet there. This is because as it passes through the magnetic field, then due to the fact it's a moving conductor in a magnetic field, we get induced currents in this aluminium plate. The direction of those currents you could work out from Fleming's right-hand rule, but because then you've got an electric current within a magnetic field, then that electric current within a magnetic field will experience a force. This is due to Fleming's left-hand rule. So there is a force on that aluminium plate. The induced current causes a force on that aluminium plate because there's a current flowing in a field. Now, from Lenz's law, we know that the direction of the induced current will be such that to oppose the change that produces it. So the direction of that induced current is in a direction so that the force on the conductor slows it down. It acts against the magnetic field. So the magnetic field, the magnetic field here starts to either attract or repel depending on the motion. But either way, it slows down the aluminium plate as it's moving. Similar example with this is the magic trick, we always call it. If you drop a magnet, quite a strong small magnet, down a copper tube. Now copper is a conductor, it's a very good conductor with a low resistance. As this magnet moves relative to the copper tube, then there are induced currents within the copper tube. Those induced currents act against the change that causes it, so they actually slow the magnet down. They would be repelling the magnet, if you like, so it stops it falling as fast under gravity as it would under gravity without the copper tube being there. And the whole thing, it takes longer than would it be expected to fall through the copper tube. It's quite strange when you see it. But both of these are examples of eddy currents. Okay, so what are eddy currents? There will be induced currents whenever the flux linked with a conductor of any shape or size changes. If the conductor is not a wire, then these induced currents are referred to as eddy currents. So we call eddy currents as any induced current that's not in a wire. Lenz's law must still apply. The induced current effects oppose the motion produced in them, so you get this kind of resistance effect in slowing things down if the thing's moving. It can cause problems. Low resistant paths in a metal mean that currents can be high. There's a heating effect of I²R, and some uses, if it's something that we're trying to put to use, there's magnetic braking, which we'll look at a couple of pictures of. You use it in slot machine coin identification, and some of you may have at home induction heating hobs, where these are the special hobs you use in your kitchen that don't feel particularly hot to touch, but when you put a pan on there, they cause the pan to get very hot. So here is the braking you might have seen. Roller coasters use this type of braking, so you have conductors moving in a magnetic field, and it will slow things down due to the effects we saw on one of the first slides. This would be an induction hob. So the changing magnetic field, if you put alternating current through these, the changing magnetic field, when you put a pan on top, then that pan has a changing magnetic field in the pan. The pan's a conductor, so you get eddy currents in the pan, and the pan will start to heat up. For those of you who've got this type of hob, an induction hob, you have to use special pans, and you want pans with as low resistance as possible to get the highest current as possible to get the most heating effect. Finally, there is a concept of this idea called back EMF in motors, and it's exactly to do with Lenz's law. We've looked at a motor. If you remember the motor, you've got a spinning conductor in a magnetic field, and really because you've got that, an EMF is induced in the coil by its spinning in a magnetic field. According to Lenz's law, this must act against the supplied potential difference, which is the thing causing it, and this is referred to as back EMF. And funnily enough, it tries to stop the motor from spinning, so you get an induced current that's in the opposite direction that you want it to be, and this will try to stop the motor from spinning. But at low speeds, now if you think about a motor, if you've ever used a drill or something like that, when the drill's under load, when you're drilling through the wall, the motor will reduce in speed. So at lower speeds, you have a high current because the motor's doing a lot of work. So with a high current, the induced back EMF is small. Then there's a high current coming through the wire, but because the motor's not moving very fast, so this allows the motor to deal with the load applied by drawing more power. At high speeds, really this back EMF will reduce the current, but at high speeds the motor isn't normally under load, so it's not doing a lot of work, so the current drawn by the motor is low because the induced back EMF is very high. You've got a high speed motor, so we know that at high speed the conductors are moving very fast, so there's a greater change of EMF, greater rate of change of EMF, so the induced back EMF is going to be very high, so this reduces the current, so it allows the motor to use very little power. So it's quite a good effect. Initially when you talk about back EMF in motors, you think it's going to be a problem, but it's actually ends up reducing the current that's drawn at high speeds. But at low speeds there's minimal effect because the motor is moving at a low speed, hence the back EMF is quite small.